Okay, this is the last day of Unit 4, so it's Unit 4, Day 6, and it's even and odd functions. So there's two really big concepts here that you kind of have to memorize. So it says, recall that functions are simply rules that convert inputs into outputs. These rules then can get placed into various categories, such as they're either linear, they're exponential, they're quadratic, okay? And now you can learn other ways to clarify some functions that have symmetries. All right, this is really, 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 really important, okay? So, example 24. So we're gonna talk about these in a minute right here. These are really, really important, but we're gonna put them in easier terms in a minute, okay? Okay, so it says it's good to be able to read mathematical definitions and theorems for yourself as you advance in your mathematical studies. Look at the definitions above and try and determine what they say about their inputs and outputs for these types of functions. Highlight or underline words you find important, and then write down your interpretation of these. Okay. What this is saying is, remember, there's a negative on the inside, it's a reflection of the y-axis, and it's equal to your original function. So what that means for even functions, if you have some point, it can be any point, and it comes out to be opposite x, but y doesn't change. Okay, so it's opposite x, but the same exact y. You know that that's a reflection over the y-axis. Okay, and think back to your geometry days. When we used to say reflect over the y, you just changed the x. You had opposite x. Okay, odd functions is saying, if you negate your x, it comes out as a negation of the entire function. What that means, this one's a little bit harder, is if you have any point, it comes out opposite x and opposite y. So you have to change both signs, which is a reflection through the origin, if you can remember that from geometry. Okay, so memorize this. Even functions are if you have a change in an x, but your y stays the same. So it's like a reflection over the y-axis. Odd functions are if both your x and your y change in signs, which is like a reflection through the origin. So example 21 here. I don't know why that says example 21. I think that's an error. It should say, I think, 24. I think that's a typo there. It does. I don't know why it even says that. I have no idea why this is even there. Okay. It might be easier by looking at even and odd functions from a graphical standpoint. Consider the partial graph of the function f of x shown twice below. Sketch the other half of the function if it is even and if it's odd. So you have to memorize, guys. An even function is a reflection over the y. So literally, how would you reflect this graph over the y? Okay, this one's on the line of reflection, so it stays there. This one is 3 to the right, so you go 3 to the left. Okay, there's that part of the graph. This one is 1, 2, 3, 4, 5, 6, 7 to the right, so you're going to go 7 to the left. And there's your graph right there. Okay, if you wanted to look at these coordinates, remember, you're only changing the sign of the x. Now, 0 can't get changed. That's why the point on the line of reflection stays 0, 0. This one goes to -3, +5. And then this one goes to -7, -2. So if you notice, only the signs on the x's change. That is an even function. Odd function is a reflection through the origin, which means you have to change both signs. So something easy to do, 0, 0 can't change, that stays. This becomes -3, -5. This one becomes -7, +2. Another way is you can count how many spaces it is from the origin. Now this one's on the origin, so it stays in the origin. That's invariant. We learned that term in geometry last year. Now, count how many down and over to the origin. So this one is down 1, 2, 3, 4, 5, 3 left. So we went down 5, 3 left. So now you're going to go 3 left, down 5. Okay, there's my point, -3, -5. Okay, and then this one would be up 2 over 7. So you're going to go over 7 up 2. And there's the coordinate -7, 2. So that's what a reflection through the origin looks like. Part C says, describe the symmetry of the even graph and the odd graph. Use as technically correct terminology as you can. Okay, so for even functions, it is symmetric to the y-axis. Meaning if you folded that picture right on the y-axis, it would mirror up. It would be a mirror image. And odd functions are symmetric to the origin. If they're symmetric to the origin, guys, that's like a rotation of 180 degrees as well. So if you turned your paper upside down, that's exactly what the picture would look like. Okay, next little page here, top of the next page. Some of the functions you have seen in your studies so far are even and some are odd, and many have been neither. Let's take a look at a variety of functions and consider whether they fall into these categories. So now, guys, remember, not every function is even or odd. It could be neither of them, okay? So looking at this, as soon as I see this, I know that I'm moving this whole graph. It's a vertical shift down 4. Okay, that's like my D and C bad. Evaluate this function for a variety of opposite inputs. See below what type, even, odd, or neither. Okay, so ready? If I put 6 in, I get 2. If I put -6 in, I get 2. So think of it this way. This one is the coordinate 6, 2. This one is the coordinate -6, 2. So the only thing that changed was opposite x. Therefore, I know that that function is even. Okay? For that to be true, it would have to work for all of them. So when I inputted 2, I get out a -2. When I put in a -2, I also get out a -2. So that's the coordinate 2, -2, and -2, -2. Again, the only thing that changed was opposite x. So I think my theory is right where it's even. Okay? Last one, if you put in 5. Now remember, guys, you're just substituting 5 in here. Absolute value of 5 is 5. 5 minus 4 is 1. If I plug in -5, I still get a 1. So I have the coordinate 5, 1, but then -5, 1. So the only thing that is changing is the x. So how do I know it's even? Because I have opposite x, but the same y. That's how I know that this function is even. Okay? Part B. Sketch f of x on the grid below without the use of your calculator. Now remember, guys, okay? The normal absolute value graph is a V that looks like this, and I'm not asking you to graph this. I'm just kind of letting you reference it real quick. There's the normal absolute value graph. I'm only shifting that whole entire graph down 4. So my vertex is at 0, -4, but I'm still moving up and over. So here's that graph. Now, remember, in order for this to be an even graph, it would have to look like a reflection over the y-axis. And it is. Because the y-axis acts as the line of symmetry. So I know it's even because it says, does it have the correct symmetry for your choice in A? Yes. Remember, in A I said it was even. And if it's even, it is symmetric to the y-axis. And it is. Okay? Moving on. Example 26. Consider the function x cubed minus 4x. Okay? So the easiest thing for you to do, it says use your calculator's table, enter in a graph, enter this function in, and then put your table. I'm going to get -15, 0, 3, 0, -3, 0, 5. 15. Sorry. It says, what type, even, odd, or neither, does it have? Well, guys, you have to pair up things where you're looking at the negative and the positive. So if I use -3, if I have -3, I have -15. That's that coordinate. But if I have +3, I have +15. So when you're comparing these 2 points, would you think that just the x has changed? No, because look, the x's and the y's changed. So you had opposite x and opposite y. But make sure you test it for another point. So maybe you go and test -2 and +2. So at -2 it's 0, and at +2 it's 0. So you can't think just the x changed here because remember, 0 can't change signs. So then maybe you go and check one last check at the ones. Okay? At 1, -1 is +3, but at +1 it's -3. And again, opposite x and opposite y. So I know that this is an odd function because both of the signs changed, opposite x and opposite y. Part C, sketch a graph of g of x using your calculator and the window indicated. Does it have the correct symmetry for what you were thinking? All right, so now I just kind of graph this thing. So these are going by 1. So here's 2. This would be 1. This would be 3. Here's -2, -3, -1. And then remember, this is a little bit harder here. So if I third this is -5. This is -10. Here's my +5. Here's my +10. If I sketch this graph, okay, remember I'm at 1, -3. Here's 1, oops, sorry guys. There's 1, -3, but I also have -1, +3. So those are the opposite points right there. And then I have -2, 0, and 2, 0. So there's that little wave. And then I have 3, 15, which is here. But then I have 3, -15, which is down here. So yes, it's symmetric. To the origin. That's why you knew it was odd. Example 27. Is this simple exponential function 2 raised to the x odd, even, or neither? Justify your argument with numerical evidence. Support yours with a graphical. All right, so ready? Just start picking a point. So if I pick f of 1, plug in 1, 2 to the first power is 2. Then you want to go pick its opposite sign. So I'm going to pick f of -1. When you put in 2 raised to the -1, you get a half. So think about that, guys. That's the coordinate 1, 2, and -1, a half. In order for it to be even, the only sign that changes is the x. That didn't happen. This completely changed numbers. And in order for it to be odd, if it was 1, 2, it would have to change to -1, -2. So this one ends up being neither. If you were to sketch this in your calculator, you're going to get a graph that looks something like this. And you can see it is not symmetric to the y-axis, and it is not symmetric to the origin as well, so therefore it's neither.